Great opportunity to hear Brian Ford, who's a student of Franz Kaschuk's. He's going to be telling us about structured streams, an approach for new transport abstractions. And I'm going to turn it over to Brian.
Thank you. It's very nice to be here. So today I wanted to talk about transport abstractions. And as I didn't just turn, okay. As you're probably all familiar with, the internet protocols currently provide basically two standard transport abstractions for applications to use, streams and datagrams. And I assume you're all familiar with their general properties. So, but I want to, in this talk, I want to propose that there's sort of a problem with both abstractions. First of all, the very simplistic version is that streams aren't quite what the applications need, whereas datagrams really don't do much of anything for the application, or just don't provide enough functionality. And of course, I want to propose a solution. So to introduce the basic idea, I want to look at how applications use conventional TCP streams, first of all. And I'm going to contrast two different approaches. The first approach I call the natural approach. And this is to use a stream to represent an application data unit or a logical transaction or logical communication activity. And I want to suggest that this approach sort of corresponds to something that Clark and Tenenhaus proposed quite a number of years ago in their well-known paper on application-level framing, and where they introduced this concept of application data units. To give an example of what this means, take, for example, HTTP 1.0, the first version of HTTP, where web clients used one TCP stream per transaction. When it wanted to make a request, it would open a TCP stream, send a request, receive the response on the same stream, and close the stream. If it wants to make multiple responses to multiple transactions to get the images on the page and stuff, it opens additional requests, either additional streams, either sequentially or in parallel, depending on what the application is trying to do. So this approach has some nice sort of semantic advantages. First of all, it ends up falling out that TCP provides the application reliability and ordering within a transaction, while keeping different transactions independent and ability to operate in parallel with no interdependencies. And again, to bring up this idea of this being sort of representing what an implementation or expression of what Clark and Tenenhaus might have been having in mind. I haven't actually been able to ask them in person yet. I would like to, but with the idea of application layer framing. Unfortunately, this approach to using TCP has a lot of serious disadvantages. They're all practical. First of all, you have a serious setup cost, setup delays, the three-way handshake at the beginning, followed by slow additional round-trip delays to get the congestion control slow started. After you close the stream, you got to keep the state around for 4 minutes, at least on one side. And then it has costs in the network, in state, in middle boxes, network address translators, and firewalls. And of course, finally, if you've got an application that uses 10 concurrent streams, then that application is being 10 times as aggressive as the application it's competing with that's only using one stream.
Point?
Yeah?
I'd like to propose that these are not disadvantages of the method, but disadvantages of TCP.
Yes, I completely agree. And so in contrast, so because of these disadvantages, people don't use that natural approach. Instead, people use what I call the practical approach, which is to use a TCP stream as a session. So for example, the quintessential example is like SSH. The client opens up a connection, does a bunch of commands and responses and throughout an entire session. But most protocols these days actually use this approach. Like email, the POP client connects to the server, downloads a bunch of email over the same TCP stream. Current HTTP 1.1 browsers do the same thing. They open one or two TCP streams and then successively use that stream for a bunch of different requests. So this, nicely solves the practical difficulties of the natural approach by amortizing the costs of TCP streams across many application data units or many transactions. Unfortunately, it sort of blows away some of the nice semantic features we had with the natural approach, in that TCP's reliability and ordering now applies across many application data units instead of one, and there's nothing the application can do about that. So this creates unnecessary serialization. If the application is putting multiple things on the same stream, the things that come later have to wait until the things that are before to get through the pipeline. And this creates head-of-line blocking problems too, where if one packet gets lost somewhere in the TCP stream, everything behind it has to wait. And this is why, for example, delay-sensitive media streaming, over TCP is a bad idea. And it's also why it was discovered that, at least in some cases, HTTP 1.1 made web browsers appear or feel slower to users than they did with HTTP 1.0, even though they make more efficient use of the network. And finally, of course, it just makes applications more complicated because they have to deal with multiplexing lots of transactions and pipelining and stuff like that. And for example, just witnessed HTTP 1.1 pipelining, which still isn't widely used 7 years after the spec came out, because some servers just can't quite get pipelining right. So obviously we can always scrap TCP and just have the application use datagrams. But of course, then the application really has to do a lot itself, and this leads to complexity, fragility, duplication of effort in application protocols. There's a lot of this stuff that is really common to lots of different applications. We'd like to share that across applications, and so I want to propose that we don't actually give up on TCP. We just fix it. We don't give up on the stream abstraction. Fix the stream abstraction. And so I'm going to propose these three basic goals for what we would really like out of streams. First of all, the streams should be cheap. So the application can use one stream per transaction or ADU efficiently. It should keep streams independent, just like in the HTTP 1.0 model, so that the applications can take advantage of natural parallelism. And since I'm proposing that the applications are going to end up using a lot of streams, we need to make sure they're relatively easy to manage, so the application doesn't have to go through the whole bind, allocate IP port numbers, authenticating separately each new stream and stuff like that. It should be simple to use. And so to satisfy this, I propose the idea of structured streams. What is a structured stream? Well, basically, it's a TCP stream, except with a fork function added, sort of like you do with Unix processes, except now you do that with streams too. So, say a web client opens a connection to a web server. This is a top-level connection, and then it decides it needs to download some pages. It sort of forks off of the top-level connection a child connection, a child stream. For a given HTML page, for example, and then within that HTML page, as it's downloading the HTML, it finds some images. It forks off some grandchild streams to download those images. This is just an example to give you an idea of the model. And how does this specifically appear to the application in terms of API, for example? Well, basically, it's not a very big modification. As far as the application is concerned, all we're doing is giving the application to listen on on something other than a listen socket. You allow the application to listen and connect on an existing connected socket in order to create child streams from that socket. And when the application, when the initiator connects on an existing stream, the responder gets the new connection in reference to the corresponding parent stream, so that the transport maintains the association between parent and child across the initiator, between the two hosts. So that's the basic idea. Now I want to dive into what this actually means as far as implementing this idea in a transport protocol. How the SST protocol is designed to support this efficiently. I'll briefly talk about the current prototype implementation, evaluation, related work, and a little future work, and finally conclude. So the SST protocol provides a number of transport services. Some of these services are provided independently for each stream. In other words, each stream gets ordering, reliable delivery, and flow control, receiver-directed flow control, independent of every other stream. Whereas other transport services are shared among all the streams, such as congestion control, replay and hijacking protection, and SST provides optional transport layer security, although I won't have time to talk about that. So what does this mean in terms of the structure of SST? Well, SST is divided sort of into two general layers. The most important components are what I call the channel protocol, which creates a sort of intermediate level transport abstraction, which implements the parts of the transport. It implements the transport services that are shared among all streams. And then on top of that, we build the stream protocol, which implements the transport layer services that are provided individually for each stream. To give you an idea of how these abstractions play out in the network, SST assumes that at the bottom level, at IP or UDP level, it has just an unconnected packet-oriented delivery service of some kind to work with. And on top of that, the channel protocol builds a connection-oriented but still unreliable packet delivery abstraction that implements these common transport services like security, congestion control, things like that. And then finally, the stream protocol takes all the application's streams and multiplexes them onto one or at most a few channels. And channels actually potentially have a long but limited lifetime, and so the stream protocol may sometimes have to migrate streams from one channel to another, although I probably won't have time to talk about that much here. Yeah?
So are you aware that there's nearly 100% similarity between streams in this picture and X25 virtual circuits?
No, I wasn't aware.
Check it out.
Okay.
Right. It's only 40 years old.
Okay. Thanks. Yeah. So just to provide an idea of sort of the mechanics of what an SST packet looks like on the wire, basically it starts with a channel header, which contains information like identifying the channel, packet sequencing, and acknowledgement information to provide the congestion control support that's implemented in the channel protocol. Then followed by a stream header that the stream protocol controls, which identifies a stream within a channel, provides flow control and byte sequencing and stuff like that. Finally, the application payload and the message authentication check provided by the channel protocol. So I'm just going to touch on a few highlights on the channel protocol before diving into the stream protocol, which is, I think, the most interesting part as far as what's unique with SST. So I'm just going to introduce the aspects of the channel protocol that are important to understand how SST works. So the main important things it provides are sequencing, acknowledgement, and congestion control. So the channel protocol assigns us a fresh sequence number to every transmission, including acknowledgements and retransmissions of old data. So in this respect, it operates a lot like DCCP if you're familiar with that protocol. Oops. It also includes acknowledgement information in every packet. All acknowledgements are selective. You don't acknowledge a cumulative point, but you only acknowledge specific packets or specific ranges of packets that you've received. Each packet contains fields to acknowledge exactly one sequence range. And typically, as the receiver accumulates packets in sequence, it sort of builds the range and sends overlapping acknowledgements, which provides redundancy against lost acts and stuff like that, without actually incurring the complexity and protocol header overhead of dealing with variable length SAC headers and stuff like that. So I'm just trying to provide sort of the benefits of SAC without all the complexity. And finally, using this acknowledgement, this sequence numbering and acknowledgement information, the channel protocol implements congestion control so that all of the streams that get multiplexed onto a particular channel automatically share the same congestion control state. And I'm not actually going to talk much about congestion control. Currently, SST just uses more or less standard TCP congestion control. It doesn't try to innovate in that respect. The important point is just that the congestion control is associated with the channel. So with that, I'm going to dive into the more interesting part, the stream protocol itself, how we create these structured streams for the application. And sort of some of the most interesting or the most critical parts are how we create streams, transfer data on them, and then I'm going to talk about how we can emulate in SST sort of the traditional datagram, give applications a datagram abstraction as well as a stream abstraction when the application needs it. So our goal in the stream creation mechanism is to allow the application to create streams rapidly and without having to wait for a three-way handshaking delay on startup. This is a challenge for two reasons. First of all, suppose we, the transport send a create stream packet, and then without waiting for the three-way handshake, it immediately started sending data on the stream. Well, what would the receiver do if the create stream packet got lost but the data arrived? Then you've got a problem. A second problem is that how does the initiator even know how much data the receiver is willing to accept on this new stream, given that it hasn't had time to get its first receive window update yet? So these are SST solves these two challenges as follows. For the first one, it's very simple actually. Every SST packet within this first round trip time before the initiator has gotten the first response on the new stream carries both the parent and child stream information. In other words, it carries all of the information necessary. Each packet in the first round trip carries all of the information necessary for the receiver to create the new stream state and figure out what's going on, no matter which of those packets arrive and which are dropped. And to solve the flow control issue, basically we take advantage of the the hereditary relationship of streams, parent and child streams, by saying that any data the parent sends in this initial round trip before it's received the first window update is actually deducted from the parent's flow control window rather than the child's, which doesn't exist yet. So after this initial round trip, things get a lot simpler, and basically they go back to the way they are in TCP, where we have byte sequence numbers with a 32-bit wraparound, just like in TCP, and effectively unlimited lifetime. And so I won't really say more about that for now. So the other sort of interesting thing about the stream protocol is how it can, because it supports the ability to use streams in a fine-grained fashion, it allows the application to use streams in places where traditionally the application might use a datagram transport like UDP or DCCP directly. And well, why would you want to do this? I'll get to that. But in SST, SST treats datagrams as ephemeral streams. So it provides an operation called send datagram, receive datagram. But the send datagram operation is semantically equivalent to creating a child stream, sending the datagram content on that child stream, and then closing the child stream. And then SST provides an option to say, to tell it not to, buffer the data and retransmit it. If the receiver doesn't get it the first time, it's lost, and the receiver effectively gets a reset. Yeah.
When you say without buffering, do you mean the application doesn't have to worry about buffering, or no buffering?
So that's well, normally if the application doesn't give SST this indication that it shouldn't buffer the data, the SST will keep the data buffered until it receives acknowledgments that the receiver has actually gotten those. So it provides, reliable TCP-like semantics by default.
It's still buffering, but at a different level.
Well, this is just an option to turn the transport buffering off on the sender, so that the transport just sends the data, and if it doesn't get there, then sorry, the receiver is just going to get a stream reset when it realizes that data isn't anywhere anymore. So, yeah. So, oh, sorry, yeah?
So, packets from such streams are still acknowledged?
So,
Packets from such streams are still acknowledged? They're still reliable?
yes, yeah. So from a normal ephemeral stream, packets everything is still acknowledged, and is reliable by default unless the application tells the sender not to buffer. But if the application tells SST not to buffer this datagram, that it should be unreliable, SST actually has the option of optimizing it a little further. So SST can take a look at this datagram that the application is trying to send and says, well, is it small? For some suitable definition of small, which SST gets to decide. If it is, SST can use an optimization in which it never actually bothers assigning a child stream identifier and creating the child stream state and destroying it and all that. Instead, it just delivers the entire datagram in a contiguous sequence of packets indexed by the channel protocol's packet sequence number, and basically sends it in unreliable fashion, much like would be done in other datagram-oriented transports. And so this makes delivery of small datagrams just as efficient, in theory anyway, as datagram-oriented transports. On the other hand, this is always the decision to do this is up to SST. So, for example, if the datagram is too large, for example, above the 8K limit or whatever limit of what it thinks will get to the other end fairly reliably, it can just choose to disable this optimization and fall back on actually creating a child stream and using it. And what this means to the application is that SST can serve as a datagram transport with no effective datagram size limit. It can send very small datagrams efficiently and also very large datagrams potentially. So there are other interesting details of the protocol, of course, that I refer to the paper, or we can talk about offline. But so yeah.
Yeah. So before we get to the implementation, just
Yeah.
to make sure I understand the semantics.
Mm-hmm.
When you don't say unreliable, you're defaulting to reliable.
When you're defaulting to reliable, what are the ordering guarantees? In particular, in a stream carries both data and forks of other streams.
Yes.
Is that a full order on the given stream of both the data and the forks of the other streams?
So within a given stream, only the data is ordered. The forks of child streams from a given stream have no ordering relationship. Different streams. So if I fork off 3 different substreams from some existing stream, then those connection attempts will still be reliably associated on the receiver with the correct parent stream, but they may get out of order with respect to each other. Just like if you initiated 3 simultaneous top-level stream initiation attempts, those could get misordered in the same way, and so.
Okay, and everything we're talking about is between a single sending machine and a single receiving machine, presumably in the normal case over a typical path, over a single path in the network.
Yeah.
So the benefit of enabling reordering would seem to only occur when there's a significant dropped packet.
So
rate.
let me address that later. I think it'll be addressed. Okay. So just to give an overview of the current prototype implementation, I've implemented a prototype in user space using C++. It's intended to be easily, linked with existing applications and portable, for easy deployability and testing. And it currently runs atop UDP rather than directly atop IP. Besides the obvious reason for this, which is applications can only get to UDP normally. There's another nice advantage of this, namely it gets across NATs and firewalls that would otherwise have no idea what to do with an SST packet. It's about 13,000 lines of code now. It's available to browse or download for anyone who's interested. And I'm not going to talk a lot about the performance. There are some information evaluation in the paper. For example, against native TCP, it sort of does what you expect. It performs reasonably well if you're over DSL or Wi-Fi kind of speeds. But if you want to run it on gigabit Ethernet or something, we'll probably want a more efficient kernel level implementation. Something like that. And it's TCP friendly, which is no surprise because it just implements more or less TCP congestion control. Then the paper includes a couple micro benchmarks and a web browsing workload, just to give sort of a flavor of what it is. The micro benchmark basically is just compares a simple request response protocol like in HTTP 1.0 over either TCP or UDP versus SST. And basically the upshot, the only take-home point of this is that at for small transaction sizes, SST sort of gives you the one round trip latency that UDP does, but it can still scale to large transaction sizes like TCP does. And then I also did sort of a trace-based simulation of web workloads based on the Berkeley trace set that's available online for basically simulating the behavior of a web browser talking to a web server, downloading web pages containing images and other things that can be downloaded in parallel, and just comparing the behavior of a naive, web client based on SST, which just sort of always uses one stream per transaction and downloads everything in, as parallel as it can, as eagerly as it can, versus different versions and styles of HTTP, the HTTP protocol over TCP. And the main point there is that it basically provides this equivalent performance as pipelined HTTP 1.1 without the application having to deal with pipelining and stuff like that. So, but the reason I'm skimming over all this stuff quickly is because I don't think that's the most interesting thing. What's interesting about SST is, well, besides the application model it provides for programming transports, it can make it easy for applications to be made more responsive. This is because SST eliminates the unnecessary serialization that TCP imposes, and also by allowing the application to create ephemeral substreams, it provides a very convenient and simple out-of-band communication method for applications. And so to give an example of one thing applications can do with this, I'm going to show how a web client can talk with a web server to dynamically prioritize and reorder requests, outstanding requests. And I'm going to show this with a little demo. So this is the SST. This is a simple web client running with SST over a simulated network, but in real time, over a simulated modem speed, like 56 kbit per second network, downloading a web page with lots of images. And currently, it's emulating the behavior of HTTP 1.1 with two concurrent streams, basically. So downloads the pages the images as it gets to them. But if the user scrolls somewhere far down in the page or clicks to a hyperlink somewhere else in the page, the user's sitting there waiting for a while. We don't like that. So with SST, it's very easy for the application to do something like just fire off all of the image requests as soon as it gets to the HTML, and then tell the web server, okay, but these are the images that are on the screen right now. Can you send those first? And if the user then changes, scrolls to somewhere else on the screen, the client can open up ephemeral substreams on the downloads that it wants to reprioritize and say, hey, change the priority of this image down and bump the priority of that image up, and give me those first. And so the application can even, do, basically whatever it wants with this, like, download the image immediately under the cursor first, and then the other images on the web page, and then other invisible images. And so, in summary, this is, I'm not going to propose that, there's no other way to do this, but the point is that SST makes this kind of thing very easy to for applications to do, and I think there are a lot of different kinds of applications that can benefit from this. Yeah?
Yeah, for the thing you just showed where image downloads were prioritized based on where the cursor was the protocol exchange that accomplished that part of SST, or is it something above it, some new thing between the browser?
That's in this case, that's just application. So it's just the client application has this JPEG download session going on, on several JPEG download streams. When the client application wants to tell the server to change the priority, it opens a new child stream on the JPEG download stream that it wants to change priority, sends a 4-byte priority change message, and the server gets that, and the server tells its SST stack to reprioritize the transmit queue basically, and so.
Did your browser already have that capability, or did you have to add that?
I had to add that. So. Yeah. So this obviously requires that the application know how to do this and how to talk to the server to get it to happen and stuff. So it's not automatic. And obviously both ends need to be running SST. Yeah.
You mentioned that you have
Should we pass the microphone around? Sorry.
Since you've got flow control per stream, could you have just used the flow control to have accomplished that by telling it to back off on the stuff it didn't want?
Well, if the server, I see what you're saying. Yes, maybe in theory, but I suspect you would see much larger delays then because if the window was is large like it typically is for normal operation, and then you suddenly slam it shut, it's going to take a while. The other side might actually fill that window before it actually responds, and so but that's a good idea actually. Was there another question over here? Should we pass the mic?
So I was looking over the DCCP and all that type of stuff, and I was wondering, what is the advantage of using SST directly as opposed to, say, implementing this kind of child stream concept on top of like DCP or DCCP that already has congestion control, things like that? Actually,
that's a very good point. That's a very good question, and the answer is there's so DC. If you look at the details of SST's channel protocol, you'll notice that there's a lot of similarity in terms of what the channel protocol provides to what DCCP provides. And it actually might be possible just to get the SST stream protocol running on top of DCCP, for example, and you would get the same effect. I mean, there are a few things that might need to be fixed or enhanced with DCCP to make that happen, and also. Obviously, DCCP doesn't provide the transport layer security that SST's channel protocol does, but that's sort of all details. I think you could probably get SST streams running on top of DCCP. Sure.
Kind of question.
The microphone.
A very similar question. In terms of alternate methods to get the same effect, you could have, if you didn't see a lot of applications for SST other than HTTP, you could simply implement out-of-order streaming, substreaming, recordization directly in HTTP.
Yes, but let me actually, I even have a slide for this, so let me go find it. Is that appropriate? Let's see.
Right. Well, actually, as it is right now, I don't think it can.
Yeah.
But you could.
Well,
but if you're willing to do a little work, I mean, it seems
Exactly.
to me it might be less work to fix HTTP than to invent a new protocol.
Yes. Oh, sorry. Yes, it might be possible. Here are the challenges, I think. First of all, you have to, in order to get good responsiveness, you have to be sure you can stop and restart, fragment, HTTP downloads and stuff into small fragments. And technically, HTTP already sort of supports that with range downloads and stuff. You could do that. On the other hand, can you just hear the screams from all the web server system administrators when they're suddenly getting peppered with thousands of small independent HTTP requests to download 1K segments of their large images at a time rather than just the whole image, or, things like that, and also just the bugs that in clients and servers that this is going to reveal. So I mean, in theory it'll work probably, but in practice I'm a little worried. Another thing is that then the application has to track the round trip time and do a bunch of sort of replicate a bunch of stuff that the transport protocol does in order to know how full to keep the pipeline. If it fills up the pipeline too much, then it's going to get long delays for reprioritization. If it doesn't fill up the pipeline enough, then it doesn't use the full bandwidth available per round trip. And in any case, you still get head of line blocking. If one packet is lost, then everything behind it gets blocked.
Okay, but still what we're really talking about is what's the best way to send 100 images in parallel without having them go sequentially. And so if you were to fix TCP or replace it by something, you could just have 100 TCP connections. Okay,
Yeah.
so morally, that's the equivalent of having 100 SST substreams,
Yeah.
or 100 X25 substreams, if
Yeah.
you will, or fixing, go to ACTP 1.9,
Yeah,
right, which
I
makes everything
completely
better.
agree, and I propose that morally that's exactly what SST is trying to do.
And I think you proved the point very well.
Okay, thanks.
So are there
Should we pass the mic?
Don't scare me. Is there anything higher level than a simple priority algorithm for kind of the mux in between the streams and the channels? Something akin to queuing disciplines, hierarchical token buckets, et
Very
cetera?
good. Yeah, very good question. I mean, there can and should be. There isn't yet. Currently, at least one point about that is, at least in the current design, the priority scheme that you use has no influence on the SST protocol itself whatsoever. There's no part of the SST protocol spec that needs to talk about priorities currently, anyway. We could debate whether maybe there should be, but if there are priorities, it's just something that the server, in this case, the server-side implementation, the server-side SST stack implements some priority scheme that the server-side application knows how to tweak to get sort of the effect at once. And then the server-side application talks to the client-side application to, negotiate what kind of priorities at once. And you could imagine doing all kinds of different priority schemes.
Right, so it seems like the TC queuing disciplines around hierarchical token buckets could be plugged in there pretty easily.
Absolutely.
Is there any support for fine-grained synchronization between forked streams?
Currently, no. Currently, once you fork off a stream, the streams are totally independent. So and a child stream can outlive its parent, for example. So again, that could be something worth considering for future work, but it's nothing like that is there yet. So anyways, yeah.
You mentioned in the intro that you were going to
Microphone.
Mike, I want to ask a question.
Oh, I'm sorry. Yeah.
So, why hierarchical? I would have thought that you could do sort of a two-level thing, two-level stream. So the top-level stream would have a different type than the sort of the children's stream, and what the top-level stream would support would be operations like fork, close a stream, change priority, things like that. And all the data transfer at the application level would always happen on the second-level streams. So you must have had something in mind which sort of made you go through this hierarchical model. And
Well, partly just partly the desire for the hierarchical model just comes from my sort of computer scientist's desire for as general as possible, as conceptually general as possible. in practice, it may be fine, to limit it to like a 2-level model or something like that. But I just didn't see any need to.
Let me rephrase it. Have you seen any concrete examples, or it'd be, say, more awkward as a programming model to live with 2 levels instead of more?
Well, it did. For example, in the web browser example, let me go back to a previous slide back here. It seemed. Oops. Yeah. Whoop. Sorry. I'm lost. Okay. So, it seems like even in like a web browser example, it's a very natural model for the, web client to sort of open up a top-level stream representing a session, and then, fork off substreams representing web pages, and off of those fork off, grandchild substreams for downloading specific content within those pages, specific images, and off of those images, fork off substreams representing priority change, out of bound priority change requests and things like that. Granted, I'm sure there's always a way the application could take a strict, if SST provided only a strict 2-level model of some kind, I'm sure there's a way the application could work around that and get, the effect the application needs, just by associating application-specific identifiers with the streams it's forking off and stuff like that. It just seemed like, it just seemed to me so natural that, the application could, take advantage of a hierarchical model, and it sort of fit into the API and the concept that I decided to go with that because of that. Yeah.
I think in your abstraction at the beginning, you mentioned a little bit about TCP friendliness. What happens when thousands and thousands of clients are doing this to 1 or 2 destinations?
Right. So to paraphrase a well-known figure in the computer science community, this doesn't solve all the world's problems, only a few of them. One of the problems it does not create
new problems. Does it create new problems?
I don't think it creates new problems. In SST, SST sort of solves the problem of unfairness of like an application, like a web browser, web server, using lots of redundant connections between the same pair of endpoints, against applications between those same 2 pair of endpoints that only use one connection. SST solves that problem. SST does not solve the problem of unfairness of, say, for example, a BitTorrent client, or where one application has 20 different connections hammering the network to completely different destination hosts, and competing against an application that's just trying to get a TCP download over one connection. And same on the server side. If the server is talking with thousands of clients, SST doesn't really provide any new answers as far as making congestion control more fair. And I think that's sort of a problem that fundamentally can't be dealt with purely at the transport protocol level, just because the transport, at least in this conception of transport protocol, that transport just doesn't see enough of the universe doesn't have a big enough picture to solve that problem at a larger scale. So.
Could you say a little bit about some of the implementation complexity? In particular, it seems as if your channel layer is roughly isomorphic to a TCP/IP layer, but that there's the potential for substantially greater synchronization load and fine-grained data structures at the stream layer, particularly when an ephemeral child is stealing from its parent's receive buffer, and you need to make sure that the parent then doesn't cause an overrun. And I wondered, if you were running this on a 10 gig link, would you suddenly see potentially synchronization overhead or memory sharing issues at the stream layer in the application?
Actually, that's a great question, and I think the rest of my talk will maybe not necessarily answer it, but will give us a better place to start discussing that question from. So shall I keep going with that? Yeah. So let's see, where were we? Okay, so I think we were here. So SST actually, both conceptually and in terms of protocol design respects, builds on a lot of existing work, some of which is listed here. Obviously, one of the most important sort of conceptual inspirations is application level framing, but builds on a lot of ideas from a lot of protocols, which I won't go through explicitly, but you can see all the references in the paper. So, but sort of to summarize what I think of as sort of the big picture of what SST is trying to do, we have TCP. The sort of, you could say the motto of TCP is think serially. TCP is trying to provide nice serial stream connections that provide a simple application model, for applications to deal with. SST, in contrast, is saying, well, okay, we've tried to think serially for a long time now, but now we're sort of increasingly living in a parallel world. Now we need parallel streams. We need a transport abstraction that makes it easy for the application to get parallelism and to implement parallelism at the communication layers. And so this research so far is really just the beginning. SST is very experimental. There's a lot to do, lots of holes to fill in. There's still no even fully accurate spec. There's sort of the beginnings of one on the website you can find. There are holes in the code. Obviously, we need a more efficient implementation. There's lots of additional protocol work that will probably be needed ultimately to get this really broadly applicable. And I'm just going to sort of highlight a few specific things. First of all, I showed an example of SST's normal headers before. All of those headers have fields that are a certain size, and they're sort of sized for efficiency under for network efficiency under normal conditions, but this sort of constrains how many packets, how many new streams you can create in one round trip, over a given path. How quickly you can create and destroy streams, and how many bytes you can send on a given stream per round trip. I think that this is probably okay for most normal networks, but you're no doubt going to find networks that this is not okay for, and SST won't be able to maintain the pipeline. So we'll eventually need some kind of fat headers or wide headers, sort of like DCCP does, to provide more allow for larger bandwidth delay products and stuff like that. That's sort of an obvious need, but it's also sort of obvious how to fix it. Another one is something that actually I've already gotten vociferous demand for from certain people in the community is what SCTP calls chunk bundling, basically being able to bundle multiple small stream segments into one channel protocol packet in order to use the network more efficiently. So a more far out long-term thing, which actually starts to get toward answering your question, is looking into what I call widening the endpoints. What happens when the endpoints become multi-core processors with lots of NICs, lots of IP addresses? What can you do with it? What can the transport protocol do with those? And SCTP has already sort of explored this by providing this notion of a multi-homed transport, where the logical transport can have multiple endpoints and multiple paths between two endpoints, which can be used for failover. And there's actually was some research done in extending this in the context of SCTP for actual, simultaneous multipath transmission and stuff like that. Obviously that's useful and an important thing to be able to do in the future. And extending even further beyond that, we can obviously envision, a company like Google, for example, having, huge server farms of, machines that want to behave want to be seen by clients as, one big logical TCP, or one big logical, transport endpoint, even though there are really a lot of machines that need to share load dynamically in different ways. How can we address that? And I'll just say up front, I don't really have any definite answers yet, but I just want to point out a couple aspects of SST's design that I think would facilitate these kinds of things. Namely, this channel stream division. The channel represents a path. A stream represents the application's logical communication activity. And there's a many-to-many relationship between them. There already is actually in the current implementation, although the current implementation doesn't really ever associate streams with multiple channels at once. It's already designed so it can be in the future, and that's sort of the intent that you can associate a channel with a stream with multiple channels, a channel with multiple streams, obviously, and do things like that. And so sort of the two key points regarding this are that because the application is using many streams, and these streams can be associated with a variety of channels, possibly just one at a time, possibly a few at a time, it at least creates the latitude for the transport designer. It creates the possibility of designing the system in such a way as to avoid putting severe parallelism bottlenecks at any of these particular in the implementations of any of these particular objects. Unlike TCP, for example, where if you've got one stream and the application needs this to be one stream, then on each end you're going to have locks at the end of that stream, and that sort of, and the byte counter for each stream sort of has to count in lockstep, and you've got central points there. Actually, in another sort of particular way in which SST's design facilitates multi-homing and this kind of parallelism is the fact that congestion control is automatically per channel, they're thus per path, and so you don't have to worry about confusing the congestion control algorithm because of the varying delays of different network paths and things like that. And so those are just a couple of considerations anyway. I'm sure there are plenty more that I've missed, but there's a lot more work and thought that needs to be done. And so that's what I have. Yeah.
So have you already automated the muxing between a stream and multiple channels in the face of differential congestion on those channels, so that the stream priority will automatically choose the appropriate uncongested channel?
No, in the current implementation, there's no load balancing per se. The current implementation allows a stream to be associated currently with just 2 channels at a time, although that's easy to change. The immediate motivation for that is to allow a stream to migrate from one channel to the next. When the old stream goes dead, we sort of want to get it connected, hooked up to a new stream before that, and migrate. But the internal wiring is sort of there to enable streams to be associated with more than one channel, but it doesn't actually really take advantage of that yet.
There's usually a little bit of a tricky control loop issue
Definitely.
when you start interposing that automation.
Absolutely, there are a lot of issues it adds. So.
What happens if the application sets up 10 million streams?
Another very good question. So this is actually an area where the SST protocol another thing I didn't mention that where the protocol probably needs to be extended. Currently, the flow control only deals with bytes essentially, and I think the protocol needs to be extended to provide some kind of flow control not only for bytes within a given stream, but for to count the number of substreams that get created on a child stream, so that the server can, for example, set a queue limit for the number of child streams that can be created at once, on a given parent stream or something like that. And that's not done. That's not there yet.
I want to make sure I understand the abstractions here. Your channel abstraction, like the existing TCP stream abstraction, is bidirectional. Is your stream abstraction bidirectional?
Yes. The stream abstraction looks exactly like a TCP stream as far semantically, other than with the addition of being able to fork child streams and the subtraction of TCP's vestigial out-of-band mechanism, the TCP's urgent flag.
Have you thought about whether there is any advantage in supporting unidirectional streams?
Actually, it seemed like I did think about that at one point, but I can't remember what conclusion I came to, if any. So I guess the answer is no, I haven't thought about that much. But actually, I think I was pondering at some point whether something like SST could ever be used in a multicast model or something like that, and that would be an example of where that could be used, but I haven't really explored that in any depth. So.
Okay. And have you thought about a three-machine interaction where machine A sends to machine B a fork of a stream that it has to machine C?
Yes, I have thought about that some. There's obviously some extensions to the protocol, and some work that would be needed to be done to support that. But actually, that's something I'd like to do. And in fact, one of the aspects of SST that I didn't have time to talk about is the way it detaches and attaches streams to different channels. It uses a sort of besides the small stream identifier that it uses to identify a stream within channel, SST has sort of a larger global stream identifier that it uses to attach streams across channels. And you could, with some suitable authentication and mechanism and stuff, you could envision that operating in such a way so that streams could actually be handed off among machines. So.
Okay, I think we're out of time, so let's thank Brian for the talk.
Thank you.
Very much.